Linear programming is a mathematical model that allows you to maximize good outcomes or minimize bad outcomes in a set of linear constraints. In this case, we have a school board that is trying to maximize um, the number of student graduates. So let's start by splitting out the different linear constraints involved in this exercise to try to figure out how to maximize the number of students that are graduating. So let's call teachers X and aides Y, and then try to determine what the maximum amount of graduates we can get with that constraint. So that would be 8x, 8 times the number of teachers, 6 times the number of students equals the maximum graduation rate. Then for the second constraint, we would have the number of teachers times 1,500 plus the number of aides times 1,000 will equal the budget of 50,000. 12 teachers just means x is larger than or equal to 12, and 20 faculty just means x plus y is larger than or equal to 20. And a ratio of at least one teacher for every 2 aides. So that's basically the mathematical constraints that we have here. Now let's convert each of these equations into the slope-intercept format so that it'll be easier to graph them. So trying to get y by itself on one side, we get 6y equals minus 8x plus the maximum graduates, or y minus 8 divided by 6, or y equals minus 4/3 plus max over 6. For the budget constraint, we get 1,000y is less than or equal to negative 1,500x plus 50,000, or y is less than or equal to negative 32x plus 50. There is no intercept for constraint 3. For constraint 4, we get y is larger or equal to negative x plus 20. And for the ratio, I'll clean this up a little bit, we would get y is smaller and equal to 2x. The line that represents the maximum solution for student graduates is a little bit unknown to us right now. We don't know exactly where it crosses the intercept, the y-intercept. We know that that's max over 6. But one thing we know about this line is that it has a slope of negative 4/3. So the line is going to slope down 4 and over 3 and have a slope approximately like this. Now let's plot the budget constraint. So that's our second constraint, and the budget is y is less than or equal to negative 3 over 2x plus 50. So if you set x to 0, y is going to equal 50, and if you set y to 0, x will equal 50 over 1.5, which is 33 1/3. So let's go ahead and plot those two. So when x equals 0, y equals 50, and when y equals 0, x equals 33 1/3. So that's the point there, 33 1/3, 0, and then the line looks about like that. Now let's go do the next constraint, the third constraint, number of teachers, which is x is larger than or equal to 12. And that'll be a point starting at x equals 0 or x equals 12 going straight up. The next constraint is the faculty constraint, which is y is larger than or equal to negative x plus 20. The minimum faculty equation is y is larger than or equal to negative x plus 20. So when x is 0, y is 20, and when y is 0, x is 20. And let's plot the point where x is 12, because we'll need that later. The final constraint is that for each teacher there can be no more than 2 teacher aides. So let's plot that. That's just 2x is larger than or equal to y, or y is less than or equal to 2x. So when x is 0, y is 0. When there's 1 teacher, there's 2 aides at the most. And then plot 10, 20, and 12, 24 again, because I think we'll end up needing that later. We've now defined the boundary of our solution set. It's below the teacher to aide ratio, the yellow line, to the right of the blue and green lines, the amount of teachers that and faculty we can have, and to the left of the budget line. We also know 4 of the 5 corners. We've solved for those as we were going along. So there's only really the corner where the budget line crosses the teacher to aide ratio line that needs to be solved. And we solve that by doing those 2 equations and 2 unknowns, basically setting, eliminating y and setting the 2 equations with each other. So that gives us 2x on the one side from the teacher aide ratio, and from the budget ratio we get negative 3 over 2x plus 50. Then solving for x, we get 7/2 x equals 50, or x equals 14 and 2/7. And then plugging x in for y, it's double that, or 28 and 4/7. So to solve for this linear program, we just use the theorem that says if you check all 5 corners, you will get one of those will be the maximum. So the first corner we're checking is the 14 2/7 by 28 and 4/7, and we get 285. Yeah, it's also, well, let's go through the other corners. So 33 1/3, 0 is a little bit less. And then 12 and 24 is even less. And then, as you might guess, 12 and 8 is less than that. And then the 20.0 is in between those 2. But it's probably equally important to understand when you look at this that essentially we have this line that represents the maximum, and the first corner it hits is that 14 by 28 corner. And when it hits that, the max over 6 is the y-intercept, right? So if you take that 285 divided by 6, you see it'll equal 47 something, and as that line moves to the left, it's always going to be a lower y-intercept. The model is also very useful for what-if scenarios on other constraints. For example, you can see the blue line, the minimum teacher line. If you have a higher number for that, that will then drive your maximum. You can see the green line, the faculty limit of 20 really has nothing, no effect whatsoever. Mathematical modeling plays a role in almost everything going around in the world today, from predicting heart attacks to predicting tsunamis and their impact, to understanding in Afghanistan where the next eruption will occur, the financial community trying to predict what markets are going to happen, the sports community trying to design new how to make cars more survivable in a crash, and even social networks like Facebook. Who's influencing who about what, and who should they target to sell other people more things? Modeling is everywhere.